How to correctly size components using stress analysis. Have you ever wondered how engineers ensure that components can handle the loads they face without failing? Correctly sizing components using stress analysis is key to achieving this. Let's break down the process step by step. First, it is essential to identify the load conditions and requirements. This means defining all the different types of loads the component will experience. These can include static loads, dynamic loads, thermal loads, and fatigue loads. Each of these loads plays a significant role in determining the stresses that will develop in the component over its service life. Next, you need to select the appropriate stress analysis method. There are three main approaches to consider. Analytical methods work well for simple shapes and loading scenarios. They provide quick estimates but may not handle complex situations effectively. Numerical methods, especially finite element analysis, divide the component into small elements to calculate stress and strain accurately. Lastly, experimental methods like strain gauging can validate the results from analytical or numerical approaches. Once you have chosen your method, it is time to build the stress model. For finite element analysis, create a detailed model that includes the component's geometry, material properties, and boundary conditions. Pay attention to mesh sizing. A mesh that is too coarse may overlook critical stress areas, while a mesh that is too fine can increase computational costs unnecessarily. The goal is to find a balance where the results stabilize with mesh refinement. After building the model, you will perform the stress analysis. Apply the defined loads and boundary conditions to the model and solve for stress and strain distributions. Identify the critical regions where stresses are highest, as these areas will require careful attention. Next, compare the calculated stresses to the allowable limits for the material. This involves looking at yield strength, ultimate strength, fatigue limits, and safety factors. It is vital to ensure that the component operates within these safe stress limits to avoid failure. Now, it's time to iterate on the component sizing. Adjust dimensions such as thickness or cross-sectional area to reduce stresses below allowable levels. Make sure to consider manufacturing constraints and minimum sizing for productivity. This may involve increasing thickness in high-stress areas or selecting materials with greater strength. Additionally, consider multiple failure modes and load cases. Sizing should account for strength failure, buckling, fatigue, and deformation limits across all critical load cases. The most critical load condition is the one that produces the highest stress and will guide your sizing decisions. Finally, validate and refine your design. After initial sizing, conduct detailed analyses or physical testing to confirm that the design meets performance and reliability standards. Make any necessary adjustments to optimize the component. This process is widely used in fields like aerospace, automotive, and structural engineering. For instance, in aircraft design, finite element analysis models simulate various load conditions to ensure that structural elements remains within safe stress limits. By following these steps, you can correctly size components using stress analysis, ensuring they can withstand operational stresses without failure. This approach is essential in preventing mechanical breakdowns and product failures in the world around us.